Okay, so today we're talking about forced oscillations of single degree of freedom systems. We're going to consider continuously or just simple Duffing oscillators, but now with forced excitation. There are really two types of excitations that one could consider. That first is known as external. This is what you've probably seen in like a linear vibration setting, where there's some external force or an inhomogeneous term acting on the oscillator. The second kind is known as parametric excitation, and then leads to the concept of parametric resonance. And a simple example of that is what's known as the Einstein oscillator, and this has the form of x double dot plus omega squared of t of epsilon t times x equal to 0. So here, this omega squared, this is a function of epsilon t. It's not multiplying epsilon t, it's a function of epsilon t. And this is known as the Einstein oscillator. And so in this case, the parameter itself, that omega, is varying with time. And so that gives us this parametric excitation. So a physical example of a system with parametric resonance or excitation, a very simple one, is that of a pendulum with a moving base. In this case, the base is moving both in terms of displacement of x and displacement of y, both vertical and horizontal directions. And in this case, the equation of motion ends up being theta double dot plus the quantity g divided by L minus y double dot over L times the sine of theta minus x double dot over L times the cosine of theta is equal to 0. And if we were to go ahead and linearize this for small oscillations, we'll get that theta double dot plus the quantity g over L minus y double dot over L. This quantity times theta is then equal to x double dot over L. And then here, the quantity in the square brackets, this is our parametric excitation. And the quantity on the right-hand side of the equals is then the external excitation. So in this case, the horizontal motion acts as an external excitation to the system, and if you add in a vertical excitation, you end up with a parametric excitation. There's a whole bunch of theory and stuff you can do in terms of like studying stabilities and resonances with parametric excitations. Particularly, you study what's known as Floquet theory. In this chapter, we're only going to look at external excitations, and we probably won't do parametric excitation in this class. We just won't have the time. All right, so in this chapter, we're going to look at external excitations. So we're going to be looking at single degree freedom systems, so equations of motion like u double dot plus omega 0 squared. It is then equal to epsilon times f of u and u dot plus some external excitation, which we'll just say is E. E is our external excitation. And then here we're going to have both nonlinear terms and damping terms as well. And they're both the damping and the nonlinearity are going to be weak. Okay, so if E draws from an energy source that is ideal, then we can say that E is just equal to E of t. In other words, it's only a function of time. It doesn't interact with the system itself. If that is not true, then the excitation itself, E, becomes a function of time, u, u dot, and u double dot, meaning that there's some kind of coupling between the excitation source and the actual structure itself. So real systems are never ideal, of course, and that means that your excitation source in a real experiment is of the form, the second equation that I've given there. So depending on how you force it, you may be able to make the assumption that the source is ideal, but that may not be true, and it depends on the equipment you're using and the type of structure you're testing. So one example is you might take what's known as a modal shaker, which are intended for relatively high frequencies, and you might try to force a structure at low frequencies. So like by low, I mean sub 10 hertz here. And what might happen in that case is that instead of the structure moving, the shaker moves itself, if you haven't secured it properly. Okay, so what is an ideal energy source? That is one that has unlimited energy, and it is totally unaffected by the state of the system. And in this case, in this course, we're just going to assume that all of our sources are ideal.
So what do you mean by ideal? Like we have an external source?
Yeah. So it's external to the system.
It has nothing to do with the system.
Yep. All it does is it provides an excitation to it. And it doesn't interact with it. It's not affected by it in any way. It's not affected by the response of the system. And then likewise, the system, besides that force, the system can't do anything to it.
Is it like a disturbance?
No, not necessarily. But we will take a look at disturbances in a moment, towards the end of the class. But it doesn't have to be a disturbance. It could be a periodic excitation. And so disturbances are like short bursts.
White noise.
Well, it could be white noise. It could, in this case, we're just going to say periodic. But it could be white noise. It could be something like that. The key thing here is that what is causing that excitation is independent of the actual system itself that we're studying. That's the key distinction we're making. Whatever the input is, it doesn't matter. It just doesn't, it's not influenced by the state of the system that it's exciting. And when you've done like linear vibrations, this is what you would have seen as well. You would have already inherently made this assumption to start with when you write down that the forcing is just cosine of omega t or something. You're inherently assuming it's an ideal source. Okay, we're going to consider just a system with cubic nonlinearity here. You could add other terms and study those as well. In this case, we're just going to stick with cubic nonlinearity. So our equation of motion is going to be u double dot plus omega 0 squared times u. This will be equal to minus 2 epsilon c times u dot minus epsilon alpha u cubed plus some function e of t. And here epsilon is much less than 1, so a small parameter. And like I said before, we have both weak damping and a weak nonlinear restoring force.
So in equation 1, when we mentioned epsilon can be anything.
As long as it's much less than 1. Oh, in equation 1.
Equation 1, there's no condition on it.
Yeah.
So here we're just looking in general form.
Well, actually, we should go back and revise that and then add that epsilon should be less than 1. Because that's what we're studying here. And although the concepts that we're studying here will transfer if epsilon is not small, the analysis does not transfer. So we're going to look at, today we're going to look at primary resonance, and we're going to see multiple solutions pop up. That transfers when you have strong nonlinearity, maybe strong damping. Typically, real structures are weakly damped, so we never really consider strong damping when it comes to vibrations. Although we probably won't get to see this, but there are cases where you might increase damping and actually get a larger response due to the nonlinearity in the system. We probably won't get to see that, though I might make like a handout or something. So yeah, in this case, in this class, up until we do, if we do complexification averaging, that every time we'll assume epsilon is weak, or is a small parameter. Okay. So we're just going to make the assumption here that E of t is equal to k times the cosine of capital omega t. So we're just assuming that it's periodic in this case, or in this case it's a cosine excitation. It doesn't have to be, but we're just going to study what happens under periodic excitation. And it can get as complicated as you want it to be. So depending on what value capital omega it has, we will end up with 3 types of resonance that can occur. We'll have what's known as fundamental resonance, which is also called primary. And in this case, we get that capital omega is close to omega 0. The second type is that of superharmonic, in which case capital omega is approximately equal to 1/3 omega 0. And the third is subharmonic. And in this case, omega is approximately equal to 3 omega 0. So we're going to look at we're going to look at case 1 today for just primary or fundamental resonance. And then on Thursday, we will take a look at the other 2 cases, or at least one of those cases. Okay, so we're going to deal with primary resonance now. We're going to make the assumption that omega 0, or capital omega, is close to omega 0. And then we're going to introduce a frequency detuning parameter, sigma, such that capital omega is equal to omega 0 plus epsilon sigma. So in this case, we can see that, well, epsilon is scaled by, sigma is scaled by epsilon such that it becomes small. So it's a small detuning away from omega 0. And then we're going to study the resonance behavior as a function of this sigma parameter. We're also going to assume that the excitation k is equal to epsilon times a lowercase k, where this lowercase k is of order 1, and again, epsilon is much less than 1. So we're assuming here the excitation is weak, and the reason for that is that a basic feature of fundamental resonance is that you're going to get a large amplitude response for a small amplitude excitation. So we're inherently building that into this assumption. When we go to do the other 2 types of resonance, we will then make an assumption about strong excitation. We'll remove this weak excitation assumption or assertion and then study what happens under strong excitation. Okay, so in this case, the equation of motion then becomes u double dot plus omega 0 squared times u, which is then equal to 2 epsilon c. Did we have a 2 up above? Yeah. Sorry. Yeah. Did I forget a negative above?
No, it's because I just heard the 2.
Yeah, I was making sure we kept the 2 in there. 2 epsilon c u dot minus epsilon times alpha u cubed plus epsilon k times the cosine of capital omega t. And that's now our equation of motion. We're then going to apply a method of multiple scales and expand this into, we're going to expand the solution into a series of increasing order of epsilon terms. In this case, because we have weak nonlinearity, and we can then go ahead and expand at the first order or the 0th order. So we have u0 of t0, t1 plus epsilon u1 t0, t1 plus so on. And we're only going to go up to t1 here. We will not need t2 But what you should generally do is start off by including T0, T1, T2, and then seeing where the equations take you. If you can eliminate, if you only have like one secular term at order 1 and it doesn't really help you that much, then you'll have to go to order 2. If you can get something interesting out of just order 1, then you can stop there, kind of thing. Okay, so in this case, T0 is simply equal to T, and then T1 is again equal to epsilon times T.
In which case we start with epsilon to the power 0.
So here we have, we have an epsilon multiplying that nonlinearity. So in this case, we are able to start with this order without the epsilon at the 0th order. If this epsilon was not there, we would then have to start at the first order.
Even though it exists with the U dot?
So the U dot does not really matter in this case.
Okay, so when we look at the epsilon, we look at the nonlinear part.
Yeah. So what matters for this method is the nonlinearity. Although if the damping is weak, then that also helps you a bit because it won't show up in the 0th order equation. Not that it can't, because you can still solve that. The real problem is when the nonlinearity shows up in whatever the highest order, lowest order equation you study is. If that's 0th or first order, if the nonlinearity is there and there's not just a linear equation starting with, then that's where this method will break down. Okay, so then expanding the time derivatives, we'll get d0 plus epsilon d1 plus so on. For the second derivative, we'll get d0 squared plus 2 epsilon d0 d1 plus so on. We can then substitute the series for u in and also those series for the derivatives, and we'll end up with a set of subproblems embedded in that single equation. We'll then break it down by order of epsilon, and it will result in d0 squared u0 plus omega 0 u0 is equal to 0. And you'll note that the forcing did not show up at this leading order, and that's because we assumed it was weak forcing. When we do the other two resonance cases and assume strong forcing, that forcing will show up at the leading order equation. All right, for the second equation, we'll get d0 squared times u1 plus omega 0 u1. This will then be equal to minus 2 d0 d1 times u0 minus 2c d0 u0 minus alpha u0 cubed plus k times the cosine of omega 0 t0 plus sigma t1.
What do you say about the first equation that we do not have the forcing?
We do not have the forcing in that equation. We also don't have the damping. And that's because we assumed that the forcing was weak, and we also have weak damping. So if we didn't have weak damping, like you mentioned, we would end up with a damping term in there, which you could still solve. It wouldn't be a problem. Also, if the forcing was strong, you could still solve that as well. But that is not something you want to do for the primary resonance case, because you're going to get a strong amplitude for even weak forcing. And then the method will end up breaking down for that strong forcing.
It is always like this? No. The thing that I don't understand, when do you, eliminate for, say, if we have strong forcing, is there there any possibility that we eliminate in some equations and we include it in some other equations?
If you want to study strong forcing, you cannot consider a primary resonance. Because the response will blow up and the equations you will derive will not be valid. Because this method is designed to work with weak nonlinearities or weak responses. If you have a strong excitation and try to study primary resonance, you end up with, I mean, you will find equations, but then when you go to like solve it numerically and compare, you'll find that your solution doesn't match what you actually get from the numerical solver. And that's because your assumptions are wrong. That's what will happen. I mean, you can solve them, but you won't get something that matches reality. Because it's violating these assumptions about, you know, the weakness of the response. And again, we're assuming that our response is a perturbation from a linear response, a small change from that, in a sense. And when you have strong forcing and consider primary resonance, you get a strong perturbation away from the linear response. So it's not that you couldn't solve it like numerically, or it couldn't happen in real life, but your solution analytically won't match. So if you're studying primary resonance, you're always going to want to assume weak forcing. If you're studying a different resonance, then you can look at strong. And you need strong to find those as well. Okay. Any other questions? All right, so we're just going to continue on. We're going to end up plugging in, well, first let's solve the U0 equation. In this case, U0, T0, T1. This will be equal to the amplitude A, T1, times e to the j omega 0, T0, and then plus the complex conjugate as well. We're going to substitute that solution for U0 in, and then collect similar terms. And I'm going to skip all of that algebra here. And what we'll end up with is minus the quantity 2j omega 0 times the quantity a prime plus ca plus closed quantity plus 3 alpha a squared a over bar, the over bar being the complex conjugate of a, and close the square bracket, and then multiplied by e to the j omega 0 T0, and then minus a, that should be an alpha, I believe, alpha big A cubed e to the 3j omega 0 T0 plus k over 2 e to the j sigma T1 times e to the j omega 0 T0. And then from here you can see that we end up with the following secular terms. First we have that big term right there, and then we have another secular term due to the external forcing. Oh, and also we got to add in the complex conjugate. So from here, we're going to collect those two secular terms, combine them into one equation, and then set them to 0 to eliminate them, which then tells us that 2j omega 0 times the quantity a prime plus ca plus 3 alpha a squared a over bar minus k over 2 times e to j sigma T1. This whole thing must be equal to 0, and we call this, we call this equation the modulation equation.
You mind explaining why those terms are circulating?
Sure. So these terms are secular because they're multiplied by e to the j omega 0 T0, which tells us that because of this omega 0.
Isn't
Sure.
that term the one that it's not circular also has that term?
This term has a 3 in the front. So here, this is forcing at 3 times the fundamental frequency, whereas these two terms here, these two secular terms are forcing at the fundamental frequency. And that's what's creating this resonance. So from here, we're just going to expand that complex amplitude into a polar form, where we'll have a real amplitude A, which is a function of T1, and a real phase B, also a function of T1 here. And this alpha here, I believe this should be A. Yeah, that should be an A. So when I originally did this, I was using alpha for my slow amplitude, and then just to be consistent with the notes from last week, I switched. And so if you find an A somewhere or an alpha where it shouldn't be, that's why. Same thing with this beta here. This should be a B. All right, so we substitute those in and we get the following. 2j omega 0 times 1/2 times A prime plus JAB B prime plus C over 2A times E to the JB plus 3 alpha over 8 times A cubed E to the JB minus K over 2 E to the J sigma T1, that's equal to 0. We're going to pull out a JB from this equation, and to do that we're going to end up having to subtract JB over here as well, and then we're going to expand this E to the J sigma T1 minus JB term. We're going to expand that into sines and cosines. So this will then give us the following. We'll get J omega 0 times A prime plus C A minus K over 2 omega 0 times the sine of sigma T1 minus B, rewrite that, sigma T1 minus B plus quantity 3 alpha over 8 times A cubed minus omega 0 A B prime minus K over 2 times the cosine of sigma T1 minus B. And then all of that multiplied by E to the JB, and that is equal to 0. From here, we're going to set real and imaginary parts equal to 0, and we'll end up with a set of 2 first-order ODEs, which are the slow flow dynamics. And so we'll end up with A prime is equal to minus CA plus K over 2 omega 0 times the sine of sigma T1 minus B. That's our first equation. And the second one, we'll get A B prime is then equal to 3 alpha over 8 omega 0 times A cubed minus K over 2 omega 0 times the cosine of sigma T1 minus B. And those are our two equations that govern the slow flow or the slow modulation of the response of this system. Okay, what we're going to do now is we're going to set gamma equal to sigma T1 minus B, and then this allows us to transform this into a set of autonomous equations, which are A prime is equal to minus CA plus K over 2 omega 0 times the sine of gamma, and A times gamma prime is equal to sigma A minus 3 alpha over 8 omega 0 times A cubed plus K over 2 omega 0 times the cosine of gamma. And so by doing this, we have eliminated time explicitly in this equation, and so we now have an autonomous set of equations. From here, we're going to study steady state response or steady state resonance solutions, and that then implies that these quantities, the amplitude is not changing with time. At least that slow modulation is not. And as a result, we end up eliminating the derivatives and get back the two equations of CA equal to K over 2 omega 0 times the sine of gamma, and then A sigma minus 3 alpha over 8 omega 0 times A cubed is then equal to minus K over 2 omega 0 times the cosine of gamma.
Tomorrow, there in equation 14, where the sigma A came from. On A gamma prime.
Sure. Give me 1 second. Okay. We'll do.
Because it's changed the B prime.
Yeah.
Okay.
So you have gamma here, and that means that B is equal to gamma.
Okay, I see. Yeah, I see where you're coming.
Yeah.
Yeah.
Okay. Cool. All right. So what we're going to do now is we're going to square both sides of these equations, and then we're going to add them together, which will allow us to eliminate the sine and cosine, and give us an equation that then allows us to find how the amplitude changes as a function of frequency. Doing that results in the following equation. We get c squared plus the quantity sigma minus 3 alpha over 8 omega 0 times a cubed, a squared actually, a squared, this quantity squared, all of this times a squared, and then this is then equal to the quantity k squared over 4 omega 0 squared. And then this is our nonlinear frequency response function. Okay, so from this equation, if we substitute in when c is equal to 0 and then k is equal to 0, which is the undamped, unforced oscillator response, we will end up with the following. Either A is equal to 0, or sigma is equal to 3 alpha over 8 omega 0 times a squared. And then we can solve for the amplitude as a function of the frequency, and we get a is equal to the square root of 8 sigma omega 0 divided by 3 alpha. And then note that a is positive, so we don't need to consider the negative of the square root. So equation 17 here defines the backbone curve for this system, for that free oscillation of the undamped, unforced system. And then we'll see in a moment how the forced solutions curve around that backbone branch. Okay, so in the case when the damping and the external forcing are not zero, we're going to then solve for sigma, which I've done in the appendix, which is at the end of your note set here. And what you find is that sigma is equal to 3 alpha over 8 omega 0 squared, or just not squared, just omega 0, times a squared plus or minus the quantity k squared over 4 omega 0 squared a squared minus c squared. And that is our equation for sigma.
Is that raised to the 1/2?
Is it in the appendix? Yeah. Yes. Make that correction. Okay, so there are cases where you might have one solution, but there are also ranges or frequencies where 3 solutions will exist, and we're going to see this in a moment. So if we come down here, this is a code for a hardening nonlinearity using this equation we just derived and then plotting for different levels of excitation. Okay, so we have increasing K going like this. That dashed black line is the backbone branch. So you can now see what I'm talking about when I say that the resonance is kind of bending around that backbone branch. And another thing that pops up is that if we just come and draw a straight line through this, we'll find that there's a solution that exists right here, one that exists right here, and then one that exists up there as well. And so we end up with these 3 different solutions. So we might be forcing at one frequency and have the potential for multiple solutions to exist. And the regime where you can have multiple solutions just gets bigger the higher the forcing as well. And for very weak forcing in that little red curve, there's no potential for multiple solutions. As you increase K in the blue, dark blue curve, there's a small region. It becomes much easier to see in the green and the cyan and the magenta curves how you can have multiple solutions that arise. All right, if we take a look here at a softening nonlinearity, in this case, the backbone branch now turns and curves to the left, indicating that the frequency decreases. So again, we have increasing K in this direction. And if we, again, just draw a straight line through this, we'll find that there's a solution that exists here, one that exists here, one that exists there. And again, we have potential for 3 solutions.
So, when we have, 3 solutions, the initial conditions define which solution we have?
No. They all exist at the same time. We'll talk about this in a moment. Yeah, we'll talk about it in a moment. Yeah, we're going to talk about it over the next like 3 pages. We're going to be talking about this. And then when we get to page 18, we'll talk more about the existence of multiple solutions. Okay. All right, so yeah.
So now I'm just trying to go backward and see where we start with sigma. And I see that we start with sigma at equation 4. And we say capital omega is equal to omega is 0 plus epsilon sigma.
Yeah.
And capital omega is related to the external force. Okay. So why do we need to find an expression for sigma? Isn't sigma something that we can change?
Right. You're right. You can find it. It is something you get to choose and change. But depending on what value you choose for it, you're going to get different responses. And that's what we're looking for, is what are the responses based on the detuning parameter? And what do you get at these different frequencies? And when we go and compute the actual final solution, you'll see that it's a constant. We end up picking this to be a single value, basically. But for right now, we're studying how does the amplitude change as a response of that detuning parameter. And so if once you have these kind of curves, if you provide me sigma, you can then determine what its amplitude could be. And it could be, in this, what I was just showing, it could be, well, like right here, it could be one of 3, but actually it can only be one of these 2. 2 of these 3, I'll say. And we'll get to that in the upcoming pages. Any other questions? Okay. So what I've done here is I have just taken a curve for a particular value of k for a hardening type nonlinearity. And we'll skip this type of analysis for the softening nonlinearity, but it's the same kind of idea. Okay, so if you had a nonlinear system and you decided to do a frequency sweep, so you have some excitation on it and you are changing that frequency of that excitation over time, and you can do 2 types of sweeps. You can sweep forward where you're increasing the frequency, or you can sweep backwards where you're decreasing the frequency. If you do a forward sweep, what will happen is we will track along this curve like follows. And then suddenly, once you reach this point over here, the response will suddenly drop down. And then follow the curve like that. This is called a forward sweep. If you were to do a backward sweep, we're tracking along the curve like this. And we'll get to right about here, at which point the response will jump up. And then this sweep will continue along the curve, following the purple arrows. So in this case, the purple is a backward sweep. And in which case this little arrow here, we can call it backward jump. And over here we have a forward jump. Okay, so what do you think, what about this curve in the center between the green and the purple curves over here? Do you think we can reach that or, achieve that level of excitation or response, I should say?
Actually, I wanted to say, I wanted to be jumped from there, a little backward.
Can you just like start at that frequency with no initial conditions?
That doesn't mean you're going to start on this curve. You will either start on this curve or this curve, actually.
Maybe it is not feasible. Some sort of physical visualization.
So it is physical. It does exist.
But the system
Is it
always
backward?
has to this region of frequencies.
Wait, can you say that again and then Prince after that?
I think this range of frequencies is maybe not feasible in the operating range of the system.
It is feasible. So, I mean, the frequency range is down here. This is our frequency range. So what I'm saying is that in this frequency range, you'll either get a response here or you'll get one on this very upper branch. Okay, so Prince wanted to say something, then Mike, you can go after him.
I was thinking maybe it's probably part of the backbone.
It's not part of the backbone branch because the backbone branch is over here. And they only, they only touch at one point. Micah?
Can you start going forward into the weird region and then start going backwards?
No. Okay, what about this side of the room?
So is the only thing determining where we're at on this, whether we do a backward sweep or a forward sweep right now? Or I guess, no?
So even if you were to just do a single frequency forcing at this level, you will get a response right here or one on this upper branch. You will not get one in the middle.
I guess what determines if we get one on just the amplitude, I guess? Which branch? we're at?
So if, depending on, if you're asking which branch, what determines which branch you start on, the initial conditions. That doesn't mean you can't switch.
Maybe it's like a combination of excitation.
Yeah, maybe they cancel out.
So you said the can't,
So, you excite at that frequency and then you hit it, at some point.
we'll get to that in a moment. You can lead to jumping from this branch to this upper branch.
Maybe it's what you're writing there. No one knows.
We haven't got to that yet.
Okay.
We do know why we can't go on this branch.
Okay.
And we probably won't do it in class. I'm going to make a handout on why we can't, showing mathematically why we can't. The reason is that these branches here are unstable. That branch, it's not branches, that one branch. We'll draw that on the next figure. Right here, what we end up getting is this hysteresis region right here. So you can compute the area that I've just shaded here in red, and you'll get some number. And nobody knows what that means physically. That's what nobody understands. You have a nonlinear hysteresis phenomena, and we as a community have no idea what that means physically. And it arises because this bottom branch, or this middle branch, actually, the middle branch is unstable. All right, let's draw that right here real quick. So I said that over here, we'll have a jump up. This was our jump over here. And I even left a little bit of the arrow there. We have another jump here. And the reason is that these solutions here are unstable, which we'll usually denote using an X. So you could start a system on this middle branch by very carefully choosing initial conditions, but it will very quickly diverge and switch to one of the other two branches. And the only way people have been able to experimentally measure this middle branch is by using feedback control and then forcing the system to stay on that through control. So if you do experimental measurements, you will get, if you sweep forward up, you will track along that upper branch. If you sweep do a backward sweep, you track along the bottom branch until it jumps as well.
Is this only true for nonlinear, cubic nonlinearities?
Yeah, that's a good question. So this kind of curvature does happen with other systems, but you have to study those, is what I'll say. Yeah, it's not a good idea to make generalized statements, but this is what you'll typically see with these. Now, the way they curve and how they curve and what they do at higher energies as well. In this case, we're only looking at like low energy, low amplitude. In this case, this is what you get to see. For the stuff that we do in our lab, those things will follow these types of curves, but multiple scales won't give you the right answer because they're strongly nonlinear. Okay. Okay, so I said we would study this soon in this little note over here, but I'm just going to post a handout on that instead. Simply, we just won't have the time. Okay. So another thing is that once we have a solution for A and sigma, we can then go and compute the phase of the system, which we'll compute using the first equation from the slow flow dynamics, which is CA equal to 1/2 K over omega 0 times the sine of gamma, in which case we can then solve for the sine of gamma being equal to 2C A omega 0 over K, which you can then invert and find gamma, and then go and find the phase B. Oh, on this plot here, this should be the phase. This should not be amplitude anymore. Okay, so for a linear system, whenever you go through resonance, you have a changing in phase of pi. So in this case, we're going from 0 to pi.
So this phase is gamma, not B.
This phase is gamma, yeah. And what did we say gamma was? Let me see. Yeah. In this case, we didn't want to include that time, but yeah. So here we solved for the phase gamma. So, okay, the red curve is low amplitude. Sorry, the red curve is the backbone, is that right?
Yes.
Yeah.
Yes.
Okay. Yeah, the amplitude on the side confused me. All right, so this is the backbone branch. This is what you'd see also for a linear system as well. You would see it jumping from from 0 to pi, basically, and you see only a single solution possible. When you increase the amplitude of k, where you add that external forcing and you add the damping, what you end up with is curves that bulge out to the side like this. And again, we'll see that there are 3 possible phases that appear here. If we consider the sine curve, we'll have some solution here, and one here. And again, we have these 3 solutions. Generally, we're not that interested in the phase. We're more interested in the amplitude of the response, because that's really what determines when stuff break, for example. If their amplitude is too large, that is what will determine if something breaks, not if the phase is pi or not pi. But again, you can also compute compute stability regions for this and determine which parts of the branches are unstable, which ones are stable. In this case, what you'd find is that along here, this branch here is unstable. Okay. So beneath that, I have the phase shown here for a softening nonlinearity, and in this case, it just bulges to the left. And again, we'll get 3 solutions.
And this one's also a phase.
Yes, good catch.
This is softening or still hardening?
This is softening. So you can see here that this alpha is -1. Okay. So just like before, if you do a forward sweep, it will follow, in this case, along like this. Reach this point and then jump up. And get another jump here. If we do the backward sweep, we'll get a jump over there. And then again, we have another hysteresis area inside here. That I don't think anybody understands either. And again, this is phase. Phase gamma.
There isn't the
So if you were to, not with the control, without control, you can't achieve this branch. And then that's a different system, which is one that we're not studying. I mean, that's what I'm saying. The hysteresis is that if you come up this way, you'll jump up here, come back, you'll jump down here. And then you can loop around this, but you can never, in this case, you can't get inside. You're forced to jump between those other, between the upper and lower branches. Okay, so this is just a phase for the softening nonlinearity. I'm just going to draw the jump loops, the jumps here. There's our backwards jump. And in this case, here's our forwards jump. And again, we get a hysteresis area inside here. And again, this is phase. Okay. So because you have multiple possible solutions existing or coexisting, what can happen is you can start on one branch and then a small perturbation can force you to another branch. So potentially you could do a test where your system evolves on the lower branch and you think, oh, the response is very low at this frequency and forcing amplitude. But the reality is that you're on the lower branch, not the upper branch. And then in operation, a small change or a small bump, for example, could then cause it to jump from that small amplitude to suddenly to a very large amplitude. And that's what I've shown here, actually. Two cases where we start in the top plot. So first on the left, we're showing a small perturbation force. This occurs at a time of 4,000, so long after the system has settled. And on the right, I have the displacements for two different types of initial conditions. One where it starts on the lower branch, and then that small perturbation causes it to jump up and jump to the upper branch, so we get this large change in the displacements. And then on the lower right figure, we start on the upper branch, and then that small perturbation causes it to drop down to the lower branch, and then evolve according to that. And so in this case, this force has an amplitude of 4, but its duration is 1. Very small in consideration in comparison to the active external force, which I'll scroll down right here. And you can see here, in this case, K is 1.2, and in this case, sigma is 1.6. So if you go back a few pages and take a look at that, frequency roughly, where was that? 1.6. In here, you'll be able to see how we have these multiple branches existing. Okay. So my point here is that because we have these coexisting solutions, these, you've got to be careful about what branch you're testing on and what you're measuring. And also what you're predicting as well. If you just do like a sinusoidal forcing and you simulate the response, you may not know which branch you're on. Okay. Any questions?
Second case is weird.
Yeah. I mean,
Like when you apply for force, you expect it to go higher, and then it goes back to the high branch. And it goes back to the low.
right, exactly. So in this upper one here, we're starting low, and that small perturbation suddenly causes it to jump up.
It makes sense.
And then here, you're applying another force, and you would expect that, it would stay the same or get higher, right? In this case, it drops.
Goes back to the
And it also depends on when you apply the force. So if you apply this at a later time, it may or may not jump. So for example, I wanted to extend, the time goes up to 8,000. I wanted it to extend to 10,000. And so I shifted it to 10,000 and I applied the force at 5,000. And this particular case would not jump, would not change. So it also depends on the time, which then tells you that it depends on, well, it depends on really what is the system doing at the particular time that you apply that amplitude. And I didn't want to investigate, so I went back to 8,000. But you could investigate these kinds of things. So yeah, there's still no guarantee that you'll jump as well. But, I personally wouldn't feel comfortable, if I did testing and I knew it was nonlinear and I found this and we were designing around this amplitude, but it's nonlinear, without knowing what the upper branch is, how do you know it's going to survive in operation? So these are the kinds of things you should think about.
So those perturbations can lead to the fundamental frequency of the system?
No, this is not the fundamental frequency. Here we're forcing at the fundamental, which I think is 1. We're forcing at 1. We're forcing at 2.6 here. That's what we're forcing at. So we're not forcing at fundamental resonance. The idea, if we go back all the way up here, of fundamental resonance from like a linear perspective doesn't make any sense anymore because, in linear case, you just have a straight line here, and therefore you have one fundamental frequency. But in this case, you can get large amplitude at multiple frequencies, and then you have this bending over of these curves. We can't study these here for this with multiple scales and for weak nonlinearity. But when you have strong nonlinearity, you can get things known as isolas, where you'll have a branch that exists by itself, like up here, or maybe over here.
I just have a question about this figure.
Sure.
So it seems everything is everything is solid black, but if we follow with time, is this oscillation?
Yeah.
So could it be that at the moment we're hitting, it's not at the high branch, like it's not at the highest level?
Yeah, potentially. I don't know. I didn't investigate, is what I'm saying. My point here is that this tiny disturbance can cause a sudden change
Yes.
in amplitude. That's the real key. This jump phenomena is what we would call this. But yeah, you could investigate that, and it will probably change with frequency as well as the amplitude of the excitation. And generally, yeah, I don't know. I've never studied the jump phenomena in terms of this kind of when should you apply a perturbation. And I'd also like to point out that, if we're thinking about a real system, you generally don't get the choice of when a perturbation happens, right? But if you have some control or you're trying to exploit this type of phenomena, you might. Again, it's tough to generalize, and it's important to study every system by itself. And then apply the analysis and see where it takes you. Okay, any other questions? We got like 5 minutes, and we're going to finish by computing the actual response of the system. And so in this case, we have some U0 of T0, T1, plus order epsilon. So we've only solved for the U0 term. We never solved for U1 because we used the order epsilon equation to solve for the amplitude and the frequency, their relationship, as well as the phase. And then as a result of that, we are not permitted to use, we don't have a U1 solution. Simple as that. We don't have that. We only have the U0 solution. And this is then A T1 e to the j omega 0 T0 plus complex conjugate plus order epsilon and above. Substitute in here, we'll get 1/2 A e to the j. Oops. In this case, we're going to have the quantity omega 0 T plus B of T1 plus CC plus O order epsilon. I wrote beta here in green, but it should be B actually. So this B here is given by that equation. We can then reduce this down to A times the cosine of omega 0 plus, omega 0 times t plus epsilon sigma t minus gamma I'll just do this quickly on the side. Earlier we said that omega was equal to omega 0 plus epsilon times sigma. And so therefore we can find that u of t is equal to A times the cosine of omega t, capital omega t, minus the phase gamma. And this is why we wanted to plot that phase gamma. So now you have the plot for A and you have the plot for gamma. You know, if you know what capital omega is, you're going to know what sigma is, and you can therefore solve for it. Okay, so you'll note here that at steady state, the response has the same frequency as the excitation, and that's why we call this a fundamental resonance. And then if you wanted to determine which of those three steady state solutions were stable, you have to do a stability analysis. And the same thing that you did with trying to find whether an equilibrium position was stable or not, that applies here as well. That's what you can do. There is another approach where you introduce a perturbation to the steady state response, and by doing that you end up with a parametrically excited system of equations that you can then solve and study using flow K theory. I'm going to make a handout on this where we use I'll go a little bit through the perturbation approach to the steady state and show how we get a parametrically excited system. But I won't solve that because we're not going to cover the flow K theory. And then I'll go through and show how you can use the technique that we've previously applied in the phase space analysis to study the stability of those three solutions. But that is the end of today.